This is exercise 5 from section 1.1 of the text. So we're given A to be any integer, and B and C are also integers that are required to be positive. Suppose that when A is divided by B, we get the following quotient and the remainder such that A is equal to BQ plus R, and the extra satisfied condition that R is greater than or equal to 0 and strictly less than B. What we want to know is what happens when AC is divided by BC. In particular, we want to show that the quotient when AC is divided by BC is Q, and that we get a remainder of RC. So if we use a division algorithm, let's write down explicitly what it is that we want so that we kind of understand what we're working towards. If we want that when AC is divided by BC, so we have AC equaling BC times some quotient, and let's call this quotient Q prime, plus some remainder, which we'll call R prime, and then we also require that this remainder R prime is greater than or equal to 0, but strictly less than BC. This question is asking then for us to show that this Q prime here is actually equal to Q in the given statement, and we're also asked to show that R prime is equal to RC. So how do we do that? The strategy that we're going to use is to use the information that we're given. And the only thing that we're given is that A equals BQ plus R, and that 0 is less than or equal to R, which is strictly less than B. So the strategy is going to be, I want to write strategy, is going to be to multiply the given equation and inequality by C. And so let's look at what happens when we do that. We're going to multiply this equation on both sides by C. So we're going to get AC equals BC times Q plus RC. And then we'll do the same thing for this inequality. And if we do that, we get 0 times C, strictly less than RC, is strictly less than BC. And note that the inequality signs are not going to change direction because we're assuming that C is positive. So let's look at what we have here compared to what we want. We want to show that Q prime is equal to Q and that R prime is equal to RC. And it looks like we have enough to do that. If we rewrite with some parentheses to show what's happening, we have that our quotient here is Q and our remainder here is RC. And that's exactly what we want. The only thing that remains is to show that the remainder RC satisfies the condition that it's strictly greater than greater than or equal to 0, but strictly less than BC. If we simplify this inequality on the right, we're going to get that 0 is strictly less than RC, just is greater than or equal to RC. Okay, last chance. RC is greater than or equal to 0. There we go. And strictly less than BC. And that is exactly what we want. So we've used the criteria from the division algorithm to show that AC equals BCQ plus RC, and 0 is strictly less than RC, strictly less than BC. And that precisely shows that when RC is divided by BC, the quotient is Q and the remainder is RC.